We are recording, but there is about 11 minutes left before we will actually start. So if you're watching this video, feel free to skip ahead about 10 to 11 minutes. Good morning.
Good morning.
Did you guys watch the game?
Yes, sir.
I watched the beginning portion of it, then had to call it quits because the kids.
It was over by the time you probably called it quits.
Yeah. I wish I cared. I didn't have a dog in the fight, so to speak.
Yeah. I went back, like, shaking up out there.
I'll have to watch the halftime today sometime. How was that? Was it a good show?
It was decent. I feel like we could see better.
Yeah.
Like, I feel like they just hyped it up. Like, it was more hype around it than what it actually was.
Very often the case.
He didn't even play, like, he played a couple of his good songs, but he didn't play, like, his top songs. Like, you figured out everybody thought he was going to play. So,
That's disappointing.
yeah.
All right, got about 1 minute left. Morning. Let's get started with attendance. Bangura, not here. Case Bolt, not here. Tristan, not here. Covington Griggs, if I remember correctly, is online, but as a reminder, you'll need to send in those attendance words before 9 a.m. Same thing with Kately, not physically here, but is online. Dow, not here. Hughes, here, is here. Lebdi, not here. Carla, not here. Mankins is here. Mathis, not here. Rains back there, right? Yep, Rains is here. Reed, not here. Elise, not here. Thompson, not here. Withrow, not here. Yendui, not here. And Elkins is here. Shut the door and we'll get started. All right. So like I said on Friday, we started chapter 3. I rushed through it as quick as I can, as quick as I could, but we didn't finish it, but that's okay, because again, none of that's gonna be on the exam. Chapter 3 was all about how cells work, and the parts of cells, and throughout these next few chapters, you're gonna learn some really important stuff about cells anyway. So, that being said, I recommend reading chapter 3, because it might introduce you to some topics that you'll need to know, or that you'll learn about in this chapter and some of the following chapters, but again, I'm not requiring. So, let's get started. The first word for attendance is actually a word, and it's just gonna be clock. But again, I am going to kind of stick with what I've been sticking with, which is for the attendance words, generally speaking, I'm going to ask you a question. And the attendance word will be the answer to that question. And again, I'll use the same examples I used last week. So for example, if I tell you biology is the scientific study of life, and then like 3 minutes later, I might say, the next word for attendance is, give me the definition of biology. So be aware of that. As usual, if you're here in person, you don't have to send me those words, but if you do, you'll get extra credit. And if you're online or you're watching the video, that is something you need to do to prove that you were watching and to get your to be considered present. Anyway, let's jump into it. So this is chapter 4. We are talking about how cells obtain energy. It's a very important chapter. If you remember back in chapter 1, we talked about the properties of life, right? And one of those properties of life was this idea of energy transformation, right? We have to be able to transform energy from one form to another. This is something that life does. So basically what you're learning here is one of those properties of life. So let's talk about it. It's broken down into energy and metabolism, followed by glycolysis, followed by the citric acid cycle, and oxidative phosphorylation. I'll give you a different word for that when we get there. Then we'll talk about fermentation, and then finally we'll talk about connections to other metabolic pathways. In short, this chapter is basically talking about cellular respiration. But before we can get to that, we need to learn some other things about energy and metabolism in general. So the first set of learning objectives are, by the end of this, you should be able to explain what metabolic pathways are, and there will be some questions about that on the exam. You should be able to state the first and second laws of thermodynamics, which will also be on the exam. You should be able to explain the difference between kinetic and potential energy, again, on the exam, and also very important because you really need to understand that bullet point to be able to move forward. You should be able to describe endogenic and exogenic reactions. That'll probably be on the exam. And then finally discuss how enzymes function as molecular catalysts. That will definitely be on the exam. To be able to understand things later in the semester, you definitely need to know that. So there's some pretty important learning objectives. It's a very important section as far as the exam is concerned and as far as understanding information to go forward in the semester.
When is our next exam?
The next exam, check the syllabus to be sure. Let me think. Should be in 4 weeks. Should be one exam every 4 weeks. Good question. And as a reminder, the quizzes are your study guides for the exam. All right, bioenergetics. Let's talk about it. I might ask you this on the exam, but probably not. At least not the definition. You probably won't get a question where I ask you the definition of them. But it is definitely a concept you need to understand. I'm only putting a question mark next to that, indicating that I'm not sure if there's questions about the definition or not. But anyway, this describes the concept of energy flow through living systems. Because like I said before, one of those properties of life is that it converts energy from one form to another. The form of energy, or the flow of energy is through a series of chemical reactions that you're going to learn about. And all chemical reactions that take place inside cells are known as metabolism. And you do need to know that. That will almost definitely be a test question. You need to know what metabolism is. It's all the chemical reactions that take place inside a cell. And this picture, I believe, is from your textbook, but it's a great, visualization of what we're talking about. Another question that'll probably be on the exam, and I think I might have this in writing in a slide that's coming up. But ultimately, with a very few exceptions, all energy on Earth came from the sun. Right? So when I don't know, who had breakfast so far today? And what'd you have? No one? Me either. Well, anyway, when you do eat breakfast, right, like let's say you're eating some cereal, something that's made from wheat. The energy in that wheat came from the sun, right? Because those plants took that sun energy and turned it into glucose and other molecules. And when you eat that, you break it down, so you release that energy, right? So ultimately, that's where it comes from. And that will definitely, or almost definitely be a test question. And a good independent work topic. So I'm saying with a few exceptions, that's where all the energy comes from. So what are those few exceptions? Also really quickly too, like I'm talking about how ultimately all the energy on Earth came from the sun. Same with this, right? Ooh, I thought I was drinking coffee. The electricity that's heating this room, that came from burning coal, right? And that coal got its energy from dead plants. And those dead plants, millions of years ago, got their energy from the sun. Anyway, any questions about that side? All right. Here we go. Let's talk about metabolic pathways. You definitely need, should I say definitely? You'll probably need to know the difference between this for the exam, the difference between anabolic and catabolic. Anabolic pathways need energy because that's how we make new molecules. So anabolic reactions build things. Catabolic reactions, on the other hand, produce energy, so to speak. They release energy because instead of building molecules, they're breaking molecules down. And when they do that, that releases energy. Both of these types of reactions need enzymes to happen. We will talk about enzymes later in this chapter. So yes, make sure you know the difference between anabolic and catabolic. And we can also put some things together here that you learned from a previous chapter that you've already been tested on. Anabolic, since we're building molecules, right, that would be a dehydration reaction. Catabolic, since we're breaking molecules down, would be a hydrolysis reaction. Anyway, any questions about that side? Okay. Thermodynamics. Probably not going to ask you the definition of it, but you need to understand the concepts. It's a very important concept. This is the study of energy and the energy transfer involving physical matter. So again, like I keep saying, ultimately all the energy on Earth, with a few exceptions, came from the sun, right? But it's not directly from the sun, usually. It has to be converted from one form to another. Like I said back in chapter 1, when we talked about this property of life, I said, how do you get energy? And some people correctly said, eat, right? We humans get our energy from eating, because we break down molecules, and that releases the energy from the molecules in the food. It's not like we can just go outside naked and absorb sun and get energy. Now, granted, you might get some adrenaline doing that, but not actual energy. So I keep using this word energy. What is energy? This is one of those definitions that I probably will actually ask you on the exam. Energy is the ability to do work or create some kind of change. Again, another great independent working topic. I'm telling you, the textbook is telling you this is the definition of energy. So you can look it up and say, you repeat that. According to the textbook, the definition of energy is the ability to do work or to create some kind of change. According to this source, the definition of energy is, when you give me the definition, then maybe write a couple sentences where you compare and contrast. There are some different, some examples of the different types of energy. I'm not going to ask you the different types of energy, at least none on this list specifically. But you're all familiar with these. Electrical energy, right? Heat energy, both of which are working hand in hand, at least right now. Light energy, right? So what you're looking at right now is coming from a light that's being projected, right? That's light energy. Chemical energy, again, there's chemical energy stored in coal, and that coal is burned, right? Which provides heat energy, and then that heat energy heats up water, which then turns a turbine, which is not on this list, which gives us mechanical energy, right? That mechanical energy is turned to electric energy, and that electrical energy is then used in this room to give us heat and also light. And again, I'm putting it next to that because I'm not necessarily going to ask you questions about the different types of energy. There are some I'm going to ask you about, and we will talk about those later. So any questions about this slide? Okay. Thermodynamics, again, we're still talking about it. The first law of thermodynamics, what you need to know, is that energy can be transformed from one form to another, but it cannot be created and it cannot be destroyed. So when you do your pre-lab in a few weeks, or a couple weeks, whatever it may be, for the photosynthesis lab, that'll be a question. It'll say something like, is the energy, what is it? In photosynthesis, are we converting solar energy to chemical energy, or are we creating energy? I think it's something like that. And the answer is we are converting energy, right? We cannot create energy. Now, granted, sometimes you might catch me saying produce energy or create energy. As a matter of fact, if you do hear me say that, feel free to correct me. But sometimes that's the easiest way to describe something. Like when we break down a molecule and it releases energy, sometimes I might say, we're producing energy by breaking down this molecule. But really, the proper thing to say is we are converting. As we learned in chapter 1, and as I said a number of times today, life depends on this conservation of energy from one form to another. Without that, there just wouldn't be life, right? We would have solar energy, and that would be it. Any questions about the first law of thermodynamics before we talk about the second law? All right, in my opinion, as far as understanding concepts in this semester are concerned, the second law of thermodynamics is less important. It states that energy is lost as it transfers from one form to another. There's a typo there. So again, when we burn coal to heat up that water to produce steam, and then that steam rotates a turbine, and that produces electricity. Every time we make that conversion from one form to another, we lose some of the energy. It's not 100% efficient. And that will be a concept we'll touch a couple times later in the semester. But again, in my opinion, probably the first law is a little bit more important as far as understanding concepts in this course are concerned. But you definitely need to know both. So are there any questions about this slide? Actually, before I move forward, this picture is pretty simple, right? Obviously, what we're saying here is that this sun energy is converted to chemical energy by plants, right? We're going to learn about photosynthesis later. But what do you think that other one, what's that saying? The one with the ice cream and then the kid on a bike. What's that mean? Chemical energy, aerokinetic energy. What are we saying there? Good, yeah. The ice cream, there's chemical energy, right? That food, that matter that you learned about in chapter 2, right? Those molecules, it took energy to build those molecules, right? And when you break those molecules, however much energy it took is then released. Because, again, energy can't be created or destroyed. So when you build those molecules, when you put that energy into building it, it's there. So then when this kid eats this ice cream and they break down, his body breaks those molecules down, it releases the energy. And then he gets on the bike and plays a little bit. Anyway, any questions about that slide? All right. Here's some topics or some, let's say, definitions you need to know. I'm not necessarily going to ask you, I don't think, these definitions on the exam, but these are concepts you must understand to understand some stuff I'm going to teach you later. First of all, heat. We've already talked about heat because when we talked about how water, the life-giving properties of water, right? One of the things we talked about was its ability to moderate heat. And at that point, I introduced you to this concept. So here we are again. Heat is a type of kinetic energy. It is the random motion of matter. Like I said before in this semester, when I say, for example, I'm turning up the heat in this room, then the temperature is increasing. What that means at the molecular level is the molecules are moving faster. That's what I mean by kinetic energy, movement, right? So heat is molecules moving, right? That is the very important bullet point, is that first one. It is also happens to be the most chaotic and disordered form of energy. Putting an X through that, not because it's not important, but for our course it is. You don't necessarily need to remember or understand that second bullet point to understand the other concepts in this chapter or this semester. What is slightly important is the third one. All energy conversions generate some heat. When I say slightly important, what I mean is there's probably going to be a question about that on the exam. And it might help you understand some concepts later in the semester. That it's not one of those big concepts where if you don't get it or you forget it, that you just won't understand other stuff. Matter of fact, I should probably redo this PowerPoint to kind of put it in order of priority. First bullet point, very important. Third bullet point, a little bit less important. Third, and then this middle bullet point, not nearly as important. Same thing with this concept of entropy. In my opinion, this is very unimportant for you 101 students. You are taking a freshman level course, not for biology majors. Entropy is very important if we're doing math. There's a lot of math involved in real biology. Like when we talk about these chemical reactions, we account for things like energy and heat and this thing called entropy. So mathematically, entropy is important, but we're not doing that kind of math in this course, so in a sense, it doesn't matter. But anyway, it's in the textbook, so I'll go ahead and talk about it very quickly. Entropy is the measure of disorder or randomness in the system. And every time energy is converted from one form to another, entropy increases. And it's really, I don't know, it's kind of hard to describe, and some people are better at it than I am. But that picture, I think, is just a great picture. And that's basically all you need to know about it, right? So here, we have a highly ordered, right? All these molecules, whatever those things are, they're put into place, and they're held together, and they fit. And then you can see towards the right, they kind of diffused away from each other. That's a concept you're going to need to know in the lab this week, right? So they diffused away from each other. Now there's more entropy on the right than there is left. There's more freedom. There's more randomness. And again, as far as this course is concerned, in my opinion, entropy is a very unimportant concept because we're not doing the math. Anyway, any questions about this slide? All right. Next word for attendance is to answer this question. As far as the exams are concerned and this course is concerned, is entropy an important topic or not? Yes or no? Entropy is important or entropy is not important? That is your next word for, your word for attendance. All right. Also, I want to point out, give this little reminder up there. This PowerPoint is largely based on the old textbook that I used. And the old textbook, in my opinion, had better order when presenting this information. So I'm just giving you a heads up right now that I'm now teaching out of order from your textbook. So if you're following along in the textbook, just be aware that I am out of order right now. Anyway, kinetic energy, you need to know what this is. It is the energy of motion. Again, another good independent work topic. I just told you the textbook's definition is energy in motion. Look it up from another source. I looked it up, and according to this source, this is the definition of kinetic energy. And write a couple sentences where you compare and contrast. Let's see if you can guess the next type of energy I'm going to talk about. If I'm talking about kinetic energy now, what do you think the other one is? So see if you can remember this from like high school, middle school, and elementary school. No guesses? Maybe it's too early. Had a long night, maybe. All right. Potential energy. Those are the two basic types of energy. All the other stuff, in a sense, as far as we're concerned, they kind of fall under those two categories. Kind of. I'm really generalizing there. Anyway, kinetic energy is stored energy. I think everyone's familiar with this. For example, you've probably seen people do this before. This is A, this is B, right? Which of these markers has more potential energy, A or B? B, right? And why is that? It's higher, right? So it has more potential energy due to its location. Most people are very aware of that. And honestly, even though that's the one that most people are very aware of, that's the one that's not really important for our course. What is important is this. Potential energy is stored energy that an object has due to its structure as well. So like I was saying earlier, this is such an important concept. However much energy it takes to build a molecule is how much energy will be released when you break down that molecule. So that's what chemical energy is. Chemical energy is the potential energy. Because again, it takes energy to build something. Energy can't be created or destroyed. So we have all this potential energy that's stored because of its structure. I'll give you some more examples moving forward. Here's a picture from the old textbook. So in this system, in this what we're looking at here, this person has the greatest potential energy when they're on top of the diving board, right? They've got potential energy because they're high, right? And then gravity, once they jump, will convert that potential energy to kinetic energy, right? Because kinetic energy is the energy of motion. Then they hit the water, then we get all kinds of different energy right there, right? You'll hear them hit the water, so that's a type of kinetic energy. Sound, you don't need to know that, but sound is a type of kinetic energy because it's the vibration of the air. Believe it or not, there's also a little bit of heat that's going to be released. That you need to know that. But anyway, once they're in the water, at this point, they have the least amount of potential energy that they'll have in this cycle. Then they fight against gravity, right? And they climb up the ladder and go up top. And as they're climbing, as they're converting the chemical energy in their cells into the kinetic energy of going upwards, they are gaining more potential energy. So that energy that they're spending, that chemical energy, those calories that they're burning to move up, is being converted to other things, but also to potential energy because they are at a higher place. Pretty simple concept, right? If you download the PowerPoint, you can watch this little animation. This is a great analogy, in my opinion, and I'm going to come back to it. The idea of a bow and arrow or a crossbow, right there. I mean, again, if you download the PowerPoint, you can watch the animation. But in this screenshot right here, there's not much potential energy, right? If he were to let go of that arrow right now, it would probably just fall to the floor. But if he pulls it back, right, it takes energy for him to do that. He pulls it back, right? Now there's potential energy. That energy, once he releases it, once he releases the bow, or the string, whatever, then the arrow is going to go, right? That energy, that potential energy will be converted to kinetic energy. And I'm going to come back to that analogy later in the semester. Actually, later today. For example, and this is a very important concept, I've already hinted at it, but now here it is in writing. Molecules have a form of potential energy called chemical energy. So I'm showing this picture of these two people trying to push together these big magnets because I'm sure you know, probably these kids, you've done this. Magnets repel each other, right? If you use like a north, south, they repel each other. And here's something, of course, it's a little bit late now because you already took the exam, but what is on the outside of an atom? There's 3 parts of an atom. What's on the, and 2 parts are on the inside. What's the part on the outside of an atom? Good, electrons. And what charge do they have? Good. So because of that, generally speaking, and I'm kind of oversimplifying here, but generally speaking, as far as we're concerned, this is fine. When you bring atoms together, generally speaking, they're going to kind of repel each other because there's negative things on the outside of them, right? So they don't necessarily want to be together, generally speaking. So however much energy it takes to push them together to make those chemical reactions happen, to build those molecules, that's how much energy will be released when you break that molecule. And not all molecules are created equal. Not all atoms are created equal. Not all chemical reactions are created equal. The harder it is to put those things together, the more energy it takes to put those things together, the more energy that will be released. That will be a very important concept later. Because again, this is chemical energy, right? It's the energy stored in these chemical bonds of these molecules. And again, like I said, I'm coming back to this metaphor, this analogy, whatever. A crossbow is a good example too, right? However much energy you have used to pull that thing back, right? It's there, it's ready. That's a lot of potential energy. And once you pull that trigger, it releases the energy, right? So it's potential energy until you pull the trigger. But that potential energy didn't come from nowhere, right? You had to pull it back. And again, I'm going to come back to that idea a little bit later. Are there any questions about the definition or the concept of chemical energy? Okay, as I mentioned in the previous chapter, this is a good analogy. This is not from your textbook. This is from the old textbook. So I'm going back to it because I think it is a good way to look at things. Cells and engines. like gasoline engines, they use the same basic process to make chemical energy that's stored in fuels available for work, right? So we can eat this fatty food. Hopefully you recognize that as a triglyceride, right? There's energy stored in those fatty acids, those big long molecules, right? Think about how much energy it took to put all those molecules together. It's there, ready to be released when you break it down. Just like the gasoline, just like the octane, that's a big long molecule. When you break it down, you're going to release some energy. And yes, the chemically, it's very similar. What happens inside of our cells is very similar to what happens inside of the engine. What we're doing is we're breaking the fuel down into smaller waste molecules. Those smaller waste molecules have much less chemical energy than the fuel molecules that we started with. And by doing this, again, we're releasing the energy, and that's used to perform work. Obviously, for a gasoline engine, that's used to turn pistons, and that'll eventually turn wheels, right? And for our cells, well, it does all kinds of stuff, but we'll learn about that later. Any questions about this slide? Next slide is a visualization of this slide. Like I said, chemically, these are very similar things. Here, we're breaking down octane in the presence of oxygen. Doing that releases heat energy. Also important for this situation is we're creating kinetic energy, right? That's what helps the energy, the vehicle move. In the process of doing that, we create carbon dioxide and water as a byproduct. Obviously, I'm not going to test you on the vehicle, but bottom part, that's more relevant to what we're talking about, right? What we do is we break down glucose and other molecules too. We break it down in the presence of oxygen. In the process, we release heat, and sometimes we use that energy, the energy that's being released to move, just like a vehicle. But more often than not, or I shouldn't say more often than that, more importantly for this semester, when we release that energy, we make something called ATP. And that ATP is then what we use to move and do other stuff. You'll learn about ATP here in a second. But again, byproducts, same thing, carbon dioxide and water. So any questions about this slide? All right, this brings us to, in my opinion, what this whole chapter is about. Cellular respiration. I'm definitely not going to ask you the definition of cellular respiration because you need to know cellular respiration. You need to know the products, you need to know the reactants, you'll need to know some of the enzymes involved in these chemical reactions. You'll need to know generally there's three types of reactions, there's three stages of cellular respiration that you're going to learn later. You'll need to know that. But yes, the book definition, at least the old textbook, is energy releasing chemical breakdown of fuel molecules. And again, I'm not going to ask you the definition. It's more important that you understand how it works than understanding the definition. Here is one number that you do need to know. So write this down if you're taking notes. Because again, I don't think this is in the new textbook. And I love, I'd like to teach out of the textbook. I don't like to teach outside of the textbook, but in this case I am. About 34% of the food energy that you take in, so about 34% of the calories, is converted to useful work. The rest of it, wasted, so to speak. It's released as body heat. You definitely need to know that number. So all the calories you eat, generally speaking, about 34% of it is actually put to use. But that's why we are 98.6 degrees Fahrenheit, right? That's what this picture is. This person's, that's a FLIR. It shows body heat. It shows heat, in that case, body heat. So yeah, 34%. Make sure, again, I just want to make sure this is very clear because I hate teaching, giving you concepts that aren't in the textbook. So I want to make it very clear to make sure you know that's not in the textbook, but you do need to know it. Also, as you probably come to realize, I'm not very big into numbers in this course, but that is one of those that you need to know, about 34%. And of course, that's according to the old textbook. So again, independent work topic. What's another source say? How much of your energy is converted to useful work and how much is wasted? See what another source says. And then again, write a few sentences about it, compare and contrast the two. All right. So here's where things get a little bit more complicated. When you're reading your textbook, don't let this confuse you. Don't worry about this. This is a 100 level biology class for non-biology majors. So in my opinion, a lot of this is not that important. We're not doing the math, right? We're not doing actual chemistry in this course. So we don't, as far as we're concerned, what I'm about to teach you is a little bit less important. But again, I'm teaching out the textbook, so here we go. So again, if you're studying the textbook and you're reading this, if you feel like you're overwhelmed because you're just not getting it, well, obviously you can come to me for help, but also understand that I'm probably not going to ask many questions about this. You do need to know what an exergonic reaction is and an intergonic reaction, and I'm going to talk about that in a second. You definitely need to know about activation energy, and I'll give you a lot of information about that. But free energy. Free energy is something that, in my opinion, is completely useless for this course, but it's in the textbook, so here I am talking about it. This quantifies the energy that is available for doing work after accounting for losses. A better way of putting that, in my opinion, is that I keep saying, right, however much energy it takes to build a molecule is how much energy is released when you break that molecule down. That's what I'm talking about. Free energy, that's what that is. Free energy is that energy that is released when you break down a molecule. Or that energy that is used up when you build a molecule. Free energy is a very important concept if you were doing these equations. If you were doing the math of biology, free energy would be important, just like entropy would be important. But we're not doing that. So you don't have to worry about it. Speaking of which, the G, that's just what I mean by that is it's a chemical reaction, and free energy is symbolized with the letter G. That's all that means. It's not a typo. Any questions about free energy? All right. Again, you do need to know the difference between exergonic and intergonic reactions, and I'm about to explain all these words that are on the board. But before I explain all those words that are on the board, here's all you need to know. And again, it's about to get more complicated because I'm teaching out the textbook, but you don't need to know everything I'm about to teach you. What you need to know is exergonic reactions release energy. Think of exert. Think of like a X, right? Like exploding or exiting, right? The energy is leaving. Intergonic reactions use energy. That's what you need to know. Teaching out of the textbook, so I'm about to give you some more details. But then what you need to know for the exam and to understand other concepts later in the semester is that exergonic reactions release energy, intergonic reactions use it. So again, free energy is symbolized with that G in a chemical equation. So when we do these chemical equations, we have something called delta G. And just in case you didn't know, when you're talking about these kind of equations, when you see a delta, that little triangle next to something, that means the change. So what we're saying there in this bullet point here is that exergonic reactions have a negative delta G, which is a really fancy way of saying energy is released. So again, not an important concept as far as I'm concerned, but I'm teaching you out of the textbook, so I'm explaining this, so when you do read it in the textbook, you're not blowing your mind. In exergonic reactions, the product have less free energy than the reactants. Again, like I keep saying, the important concept that you need to know is that you released energy. So that's why the products have less free energy than the reactants. And another way of saying this, again, not important as far as we're concerned in this class, but these are called spontaneous reactions. Usually sometimes people think of spontaneous as meaning that it happens quickly, but it doesn't. Not necessarily, sometimes they do. But again, important thing for exergonic reactions, energy is released. So let's talk about the opposite. Intergonic reactions, delta G, so the change in free energy is positive because energy is absorbed. Energy is used in these intergonic reactions. And like I keep saying, it's the opposite, right? So therefore, if exergonic reactions, the products have less free energy than the reactants, and intergonic reactions, the products have more free energy than the reactants. And again, it's the opposite. So intergonic reactions are non-spontaneous. They require an input of energy. So one last time, before I move on to the third important bullet point, exergonic reactions release energy. Intergonic reactions need energy, right? So generally speaking, exergonic reactions are breaking things down, generally, as far as we're concerned in this course. And intergonic reactions are building things. In other words, intergonic reactions are anabolic, and exergonic reactions, generally speaking, are catabolic. All right, and then finally, this more important bullet point, and we're gonna talk more about it, because it's very important. All these reactions, whether they're endergonic or exergonic, they all require some input of energy. So even if the reaction is exergonic and it's releasing energy, like a nuclear explosion, for example, that would be an exergonic reaction. Even with all that energy that's going to be released, you still need to start the reaction. And the energy needed to do that is called activation energy. It's a very, very, very important topic. Make sure you understand that third bullet point. As far as we are concerned, this discussion on this whole slide, that last bullet point is the most important. You need to know about activation energy more than free energy or exergonic reactions or endergonic reactions. You need to know that activation energy is that energy that's needed to start a reaction. And again, I'm just starting this conversation. We're going to go on and talk more about it. Are there any questions so far? All right. So for the next attendance word, answer me this question. Which reactions release energy? Exergonic reactions or endergonic? You can just say exergonic or endergonic. You don't need to put the reactions in there. So which ones release energy? Exergonic or endergonic? That is your next word for attendance is to answer that question. That being said, let's talk more about this more important concept, in my opinion, activation energy. Again, this is the energy that is invested to start a reaction. And here I am going to go back to this whole analogy right here, the whole idea of the, I can't think today, crossbow. Yeah, crossbow, right? It took energy to pull that thing back, right? And it cocks, right? So then it kind of clicks in, and all the energy that you use to pull that thing back, it's there. That's potential energy now, right? It's ready to be released. And obviously that's a lot of energy because that could be deadly, right? So when you pull that trigger, that arrow comes out at a high speed, right? Because it's a lot of energy. But it's not like it's just going to do it on its own. You have to input some energy. You have to invest some energy to start that reaction. So pulling the trigger in that case, in this analogy, would be the activation energy. It would be the amount of energy needed to pull that trigger. And think about I'm sure, I don't know if you guys have ever shot anything like that before. It's not that hard to pull the trigger, right? So you're putting some energy in, but the amount of energy you're putting in to pull the trigger is not nearly equal to the amount of energy that's being released, when that thing fires. And that's a concept we're actually going to talk about here on the next slide. But for now, are there any questions about activation? Okay. This is a picture from the old textbook. On the next slide, I'll show you a picture from your textbook, but I think this one's better. So here's what we're talking about with when we're talking about chemically, when we're talking about activation energy, because I'm not going to ask you about crossbows. Again, that's the amount of energy required to start a chemical reaction. So here, what we have here are two of the same chemical reactions. We have the same reactants here. We have the same products here. We have the same amount of energy being released, which is what this signifies. Right here, there's a lot of energy, stored energy in that molecule. There's less stored energy in these molecules because we released energy when we broke it, right? So that's what we're talking about, free energy. Activation energy, even though that's releasing energy, we still need energy to get that thing started. And as I'm about to teach you later in the next coming up slides, that's what an enzyme does. And I'm going to talk more about it later, but again, for now, I'm just introducing you to this concept. That's why enzymes are so important. Because without those enzymes, these chemical reactions wouldn't happen. And this kind of goes back to that idea of spontaneity, right? So this is an exergonic reaction that we're looking at. It's releasing energy. But like I said, technically they're spontaneous, but it doesn't necessarily mean they're going to happen on their own, which I know is kind of confusing, which is why I'm not going to test you on the spontaneous part. But again, even though they release energy, it still requires energy to get started. And almost every chemical reaction in our body has an enzyme. And without that enzyme, they all have their own specific enzyme, each chemical reaction. And without those enzymes, those chemical reactions wouldn't happen, and there just wouldn't be life. Any questions about this slide before I show you your textbook's version of this slide? All right, here we go. So this is your textbook's version. This is, in my opinion, this would be better for biology majors. So it's kind of talking about the same thing here. Here we have, in this case, we're looking at a endergonic reaction. because the products have more energy than the reactants, unlike the last one we looked at. But nonetheless, it still requires activation energy to get started, right? To get that thing going, we need activation energy. And as you can see here, it requires less activation energy when you have enzymes. Again, the enzyme thing will be important. We're going to talk more about it later. I don't really like this picture, but again, it's in your textbook, so I included it. In my opinion, if you're trying to visualize this when you're studying, you want to download the PowerPoint and look at this one. Any questions about this slide? All right, as of last week, I started doing this now. I'm doing the announcements and reminders later in the course, or later in the lecture, because on any given time, any given morning, half of the students are not here when we start. So now that this lecture is almost over, I'm gonna give you the announcements and reminders. Lab 3 is past due. Hopefully by now, as you know, I'm not very picky on the due dates with the lab. I do want to say this will be important later in the semester. That doesn't mean like at the end of the semester you shouldn't like turn in a bunch of stuff. Because yeah, you said you weren't picky about it. Like I just literally won't have time to grade it if you just turn all your late work in at once, and all the students are doing that, right? So I'm not saying that. But anyway, lab 3 is past due. Do it. Let me help you if you need help. Pre-lab 4, past due. I'm changing things up. This semester is by far the worst semester I've ever had as far as students not doing pre-labs. So many people are screwing it up. They're not doing the questions. They're not doing all the hypotheses questions. They're not doing video. It's really big. It's like, hey, don't miss this. Something's wrong. I've never had it this bad before. But I'm the instructor, so I'm taking responsibility for that. I must be doing something wrong. I don't know what it is yet. I'm going to try to fix it. But since I'm screwing this up so much, and obviously by default, that means you are too, I'm not going to keep people from coming to lab anymore because it's just not working. You guys are screwing it up, and so many people aren't coming to lab because you're screwing it up. So from now on, you can still come to lab if you haven't done the pre-lab. I don't know what I'm going to do to change things. I'll probably put you together. So if you didn't do the pre-lab, you know how we have breakdown in groups. There'll probably be one group of people who didn't do the pre-lab. So then everyone else who knows what they're doing, can move along and do their own experiments, and then those people can do their own thing. But yeah, that's the new policy. Another new policy. I still want you to turn in things the way I've asked you to do, which is turn in the pre-labs by sharing it with me via Google Docs, turning in the labs by uploading them to my online. I still prefer that. But again, this is the worst semester I've ever seen with people not being able to do that. So from now on, I don't care. Get it to me how you're going to get it to me. It's easier for you if you turn it in the way I've asked, because it's easier for me to, like if you turn in a pre-lab by sharing it with me on Google Docs, you know, I can leave those comments and say, hey, reply to this with the correct answer. You can get your points back. Can't really do that if you do it, you know, if you turn it in other ways, but whatever, that's on you. I'm here to help. Just turn it in however you want to turn it in. But, and someone had a great question last week, I want to point out and remind you, if you turn something in via Google Docs, as I asked you to for the pre-lab, and then you make changes, I have no way of knowing that you made changes. Right? So if you turn in, for example, the pre-lab the right way and share it with me via Google Docs, and then later on Wednesday you come in, you do the lab, you fill it out, I have no way to know that you've done it and I need to grade it. So keep that in mind, right? If you're not going to upload it to my online, then when you're ready for me to grade the entire lab, you need to like email me and let me know. And also, again, I hate to beat this dead horse, but this is the worst semester I've ever seen for this. So I'm also asking you to help me. How can I make this better? Honestly, I think, it's my hypothesis, this is one of the first semesters where I didn't make attendance a graded thing. It used to be 100 points of your entire grade was based on attendance. Now it's all extra credit, and now attendance is very bad, and now people are making these mistakes. Anyway, any questions about labs, pre-labs? Again, if you didn't do it yet, please do it. You're still not going to get credit if you do it late, but I'm going to let you in the lab now. Here's the big one. Exam 1 is now past due. I haven't looked yet, but I'm willing to bet someone didn't take the exam because they didn't know it was due yesterday. Whether you took it or not, you can retake the exam. Email me and say, hey, I want to retake the exam. Here's the thing with the retake. It's open book. You can take it as many times as you want. It's not timed. Just take it. And then once you're satisfied with your grade on the retake, email me and say, all right, I'm ready for you to change my grade. And then what I'll do is I'll average your first grade that you got, presumably yesterday, and then the last grade. Does that make sense? But you have to email me to let me know you want to do that. That's the catch, because so many people aren't paying attention to these lectures. Someone's not going to miss this, or someone's going to miss this, and I will repeat it again in the next lecture. Anyway, any questions about the exam? Again, one more thing. There's also nothing to lose. So if for some weird reason, every time you retake it and it's open book and it's not timed, and for some reason you keep getting a lower grade, I don't know how that would happen, but if that were to happen, no big deal, we'll just keep your original higher grade. So again, let me know if you want to retake it. This also goes for people who didn't take the exam. So if you have a 0 because you didn't take it, email me. I will let you retake the exam. Granted, even if you get 100%, it's still give you an average of your first grade and last grade. 100 and 0, that averages out to a 50. The 50 points is better than nothing. Independent work is now down to 10 points per page, like I stated at the beginning. So we're just done with the bribery on the independent work. And also, we got some weather coming in. So before you come to class on Wednesday, make sure you check your email. If I'm snowed in or something, I'll send you guys I'll post an announcement, and that'll go out to your email. Say, hey, I can't come to class. And also, if get your question in a second, if you don't want to come to class, whether we have a snow day or not, don't risk yourself coming to class. I'm going to record it. Even if I'm home, I'll just sit at home and do this lecture. We'll all meet online. So don't risk your life coming to a lecture. Yes, sir. Question?
When will we make up the lab if there's no class Wednesday?
Ooh, good question. Ooh, man, great question. Okay, so if we can't come to lab because of weather, what I'll do is, this is really crappy, but we don't have any other choice. I'll give you the data. We'll meet online for the lab, and I'll kind of pretend like we're doing, like I'll explain, like, all right, we're doing this experiment, and I'll explain how it works, and then I'll put in the data, and then you all have the data, and then you can answer the questions. It's crappy, but it's better than nothing. Great question. I'm so glad you thought of that. Anything else? All right. We do have 3 more minutes, so I do want to get this out here really quickly. Sorry. Oh, actually, next word for attendance. Let's see. Next word for attendance. At this point, excuse me. To the next word for attendance is to answer this question. At this point in the semester, how much is independent work worth? How many points is independent work worth now? That's the next word for attendance. That being said, really quickly, again, we're talking about activation energy, right? And I said enzymes are the things that allow these chemical reactions to happen with less activation energy. That's what they do. Enzymes are also very selective. That might be a test questions. Meaning, it's like you can't have like one enzyme doing a bunch of different chemical reactions. They're usually very specific. There's one specific enzyme for one specific chemical reaction, generally speaking. You're going to need to know a lot about enzymes. You need to know these words. An enzyme recognizes a substrate, and the substrate is the reactant molecule. So again, enzymes are allowing these chemical reactions to happen. The chemical reactions have reactants, the products. So it's the reactants that we call the substrate. And these enzymes, like I said last chapter, they're made of, enzymes are proteins, and proteins are it's very much about their shape, more so than any other molecule. And this is why, because they have a very specific shape where these molecules fit into it. And that is called the active site. So the area on an enzyme where the reactants basically fit in like a lock and a key, that is called the active site. The process of that happening is what we call induced fit. So when the substrate attaches itself to the enzyme, or the other way around, however you want to look at it, once those things come together, we call that an induced fit. You can see here, I like this picture because what are those people doing? Well, I don't want to ask. It looks to me like they're hugging, right? Now, I'm sure you guys know how to hug. When you hug, this is what a hug looks like, right? But this is not how you start a hug. You don't come at people like this, right? You come out to people like this, with your arms open. And then, once you're close, then you kind of squeeze, right? That's the induced fit. That's what an enzyme does. It's kind of wide open. And then it takes in the substrate. It kind of hugs it, so to speak. And that's it for this conversation. When we come back on Wednesday, or when we meet on Wednesday, whether it be in person or online, we will talk more about enzymes. And that's it. I'll be holding office hours online only. I'm feeling a little under the weather, so I'm going to actually go home for office hours and do it online. So if you need me, I'll be on in about 20 minutes at the most. That's it. Have a great week. Oh, sorry, one other thing that's slightly less important. One of your classmates who's not here was asking about, you get a 5% boost to your exam grade if you meet me online and I tell you all the correct answers and we talk about your wrong answers. But I'm not gonna do that yet because I'm allowing you to retake it, right? So you can retake this up until we take exam number 2. And at that point, you won't be allowed to retake it anymore, and at that point, I can meet you online and give you all the correct answers and your 5% boost to your grade. That's it.
Have a good day.
You too.